Okay, so in this video we're going to look at 1.2.4 data storage, and we're looking at images. So we're going to learn how computers can store images. So I'm going to skip some of this because it's a bit wishy-washy. So we'll go straight to this useful slide. So there are two main ways a computer can store an image, okay? And that means on the computer storing it. So that is using a bitmap or a vector, because in the end all images are displayed on the screen using a series of pixels, but how they're stored in the computer can be different. So a bitmap, okay, that is what you probably think of, which is basically an image is stored as a selection of pixels that are a certain color. So if I was storing this image from here, this would be the color for white in binary, white, 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 and then black, 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 white, 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 white. And that would be stored as a selection of zeros or ones representing white and black alternatively, okay? That's basically it. So that is what a bitmap is. It's a map of bits. It relies on square blocks called pixels. The quality of the image depends on the amount of pixels per square inch. So what it means by that is, if the screen is 20 inches, how many pixels are fitting in the screen, okay? So you can think of that as a resolution. When you hear about things like 4K and other things like that, 4K is actually, oh, let me memorize it. I think it is, I'll have to look it up. That's it, 3840 wide and 2160 tall, okay? So that is the number of pixels in a 4K image if you multiply those two together. And you can see that it's quite a lot. So it says 4K, but it doesn't mean there's 4K pixels. It means it's supposed to be the 4K width. It's quite a cheat, this, because they used to do things by the height, which is the lower number. So it's why, they used to say 1080p. You think, oh, that must be 1080 here because this is but actually it's not. It's a 1080 is 1960 by 1080. So they used to always use the height to denote what they call the picture, but to try and make it seem even bigger, they've gone with the width, which is a strange cheat, but there you go. So now, bitmaps are made up of pixels. Now for me drawing stuff on the screen. So, vector. What is a vector then? Because that's the only way, surely. Well, a vector, like in something like Draw Plus, is made up of coordinates and information. So, for example, if we go to transform, now I haven't got this in pixels, which is annoying. So if I set this page up into units of pixels, there we go. Right, so what you've got here for this one is an X and Y position. So I can set that X to 100, the Y to 100. I've got a width and a height. Let's set them 60, 60. I'll zoom in. And I've got, I know it's a circle. So the computer can redraw this shape at that position and using maths to get the circles. It's got an inside and outside colour and other attributes to allocate to it. Now the difference with a vector and a bitmap is it doesn't pixelate when I zoom in because the computer will redo the math to get a higher, more accurate version. So vectors are really just shapes that can be placed in, and have their attributes altered. They're not the same as a bitmap, which is essentially a map of binary data. Okay, this is just a section of things. So it might say something like circle at, whatever, like here. Draw a circle, radius is 6, there's the center, line thickness 1. And you follow those instructions, there you go. So we're going to focus mainly on a bitmap, but just so you understand the difference between a bitmap and a vector, that's what it is. So in a bitmap, at the start of every file, there's a header, like with information about the file, and that is called the metadata. So when you save a bitmap, so if I was to save this, let's save it to pictures, save it as test. Okay, then I'm going to go to pictures, right click, do properties, and I'm going to get access to the metadata. This doesn't show all the metadata, I like to add, but it shows some of it. So you can see here the metadata has got some information in it. Okay, it's got the date it was created, it's got the date modified. This is not all metadata in here, just to let you know, because this is like Windows doing a thing. You can get special programs to only show the metadata, but I should have done that maybe. But anyway, you get the gist. You can Google and look at ones. So it shows the width and the height, because the computer's got to know when there's a new line of pixels, It's got the bit depth, which will cover. It's got the file name, it's got a date created, date modified. It can have lots of different things in the metadata. It can have GPS location if you take it on your phone. It has the time and date, created, so you know when you do these things. So there's other things that can be in metadata, but it's basically it started off being like the information the computer would need to redraw the image, like how wide is it, how tall is it, how many bit depths are in there, other things like that. But now they've added more other things like the GPS location and the time and date and things like that. Okay, so that is what metadata is. So there you go. This is how they store the image. Okay, so pixels stored as black and white dots or whatever on the thing. If an image gets too blocky, if you zoom in on an image and you start to see, because zoom out, that looks pretty nicely drawn. Zoom in and it gets all blocky. That's called being pixelated. So it means where you can see the pixels. So with a bitmap, at one point there are actually just little squares coloured in. So if you zoom in enough, you will eventually see the squares. So this is why something called resolution is important, because the resolution is how many pixels are in the image. So if let's have a look. Actually, if I go on the internet and search for image in various resolutions, let's see if I can get an image. Okay, that's a terrible example, but you get the gist. Okay, so that's a better one. So if we had 100 by 100 pixels, it looks like that. And as you lower the number of pixels, it becomes more of a blur and a mess. Obviously, this is designed to demonstrate that. Even here, it's very hard to see. You may have seen some pictures of games shown at different resolutions, where they split the screen in half and show the before and after. But anyway, the point is, the higher the resolution, the more pixels there are. The more pixels there are, essentially, the smaller they have to be, in theory, when they're destroyed on the screen. And so basically, the more pixels, the better. But, of course, the file size will be bigger. So where it says what effects increase in resolution have, well, you get a bigger file size. You do obviously get a better quality image. And as you can see here, even that 768 image here with this is 1 million pixels. So just understand that high resolution is better, but it does mean bigger file size. So the resolution is the number of pixels. Now we're getting on to a little tricky one, which is called color depth. So for each pixel, so let's get a grid up. Let's assume this is an image. Excel's quite good for sort of pretending to be an image. Right, so let's zoom in to say, I'm going to do this bit. Right, in fact, I'm going to, do you know what I'll do is I'll get rid of the grids on the rest. No border, and then I'll put in, let's do an 8 by 8 image. 1, 2, 3, 4, 5, 6, 7, 8. Right, there we go. So this is an 8 by 8 image. I know they're not square, but I don't care. Actually, I do. 24, and then 24. Right, so let's colour this image in. I'm going to colour that in, and then I'm going to copy and paste and paste and paste and paste and paste. Right? Now, this image has a colour depth of 2, because there are 2 colours. So the colour depth is about how many colours you can have, but it's represented in bits. So even though this is a colours, sorry, that's not colour depth for 2. It says 2 colours. I'll just put colours 2, right? So it has 2 different colours in it. So if we go back here, we can use 1 bit to show 2 different colours. So the colour depth of this is actually 1, because a 1 colour bit depth means we can have a 0 or a 1. That's what you got. If you've got 1 bit, you can either have, if you've got a single bit of information, the 2 options are 0 or a 1. So the 0 could be white and the 1 could be black. So that would be 1, 0, 0, 0, 0, 1, 0, 0. And that would be that image, because you've got a, let's set the text to white. There you go. So that would be the binary representation of this image if it had a color depth of 1. So we've got the amount of colors available is always 2 to the power of that number. Well, so if you have, so let's add some more colors to it. Let's add that and that. Let's add 5 colors and do it really awkward. All right, so now we have 5 colors. So the way to work out how the color depth is, right, is to think about how could we display the number 5. Because let's think what we've got here. We've got, let's say 2 is yellow, 3 is red, 4 is purple. Right? So we've got 5 colours, 0 to 4. So what you do is, you think, right, well, 0, that's going to be, what's the highest number that we need? Right, 4, because 0 is 0, right? So how do we write 4 in binary? Well, 4 in binary is 1, 0, 0. So we can write these all out if in binary. So there we go, 010, dum 001, and dum 0. So that's the binary for each the colours, right? Now, we see that we need 3 bits to represent the number 4. So the colour depth for this image is 3. Because we would need 3 bits to represent each different colour. So that's what colour depth means. The more bits you allocate, the more options for colours you have. Because obviously, if you have, and the way to work it out is you can just do 2 to the power of the number, like always. So actually, with 3 bits, although we actually only use 5 colours, 2 times 2 times 2 gives us 8 colours. Because if you think about it, the highest we could type is 111, and that would be the number 7. So therefore, we could actually have colours between another 3 more colours, 5, 6, and 7, with a colour depth of 3. So that's what colour depth is. The higher the colour depth, the more options for colours there are. So 3 allows 8 different options, as we saw a second ago, 0 to 7. 8-bit allows 256 colours, because the highest with an 8-bit number is 255. And 24-bit allows, that should be 16, they've missed off a 1 there, 16 million colours in it. Right? And I'll tell you now, they don't really go above 24-bit. You will see 32-bit images, but the other 8 bits is actually used to represent how transparent a pixel is, rather than any more colours, because the human eye really can't see any higher than that many colours. So even though you might see a 32-bit image, it will still be 16.7 million colours, but each pixel has a transparency value, which allows you to lay pictures on top of other pictures and how much see-throughness each pixel is. Okay, a PNG is a great example of a format that allows transparency. So if you save an image as a 32-bit PNG, you've got the 24 bits for the red, green, and blue, and then you've got the transparency and the other bit. Okay, so the greater the color depth, the more realistic the colors. If you want to see a difference between color depth, let's have a look. Images in various color depth. And yeah, you'll see here, when you haven't got as many colours, it either has to guess a colour, or you get this thing called banding a lot, which is basically where there's not a smooth transition between colours, because you simply don't have enough colours to have an in-between those. So you end up with these sort of bands of colours. There you go. You get this a lot with lower colour depth. So that's what colour depth is. Okay? So that's in bitmap images. Now, when you get to 24-bit, so this is slightly different, because think of this is if you had like a palette. So if you could say, right, that these colors represent different things, but when it gets to 24-bit, you just store the colors in their red, green, and blue, right? So you don't say like 74 is white, 68 is green. When it gets to 24-bit, because 24-bit is like all the colours, because we don't need any more, they just store them as red, green, and blue. So it's the amount of red. So you have 8 bits to represent them. 1 byte for red, how much red there is, 1 byte for how much green, and 1 byte for how much blue. And this is called direct colour. So in the previous version, what we were doing here, we were using colours, and then we were saying a little table that said what those colours meant. Right. That's not the same when it gets to 24-bit, because there's just no point, because you might as well just say what the colours are. So then what happens is now you have a red, green, and blue value. So the red, green, and blue value for white is 255, 255, 255, because that's all red, all green, all blue, because that's how white's made. So each pixel would just have the binary, for 1 byte for the red, 1 byte for the green, and 1 byte for the blue. So in a 24-bit image, each pixel is 3 bytes, because think about it, 24 divided by 8 equals 3. So 24 bits for each pixel. So each pixel with the screen would be 3 bytes of data. If you have, like it does here in this example, the alpha on the 4th channel, which is called RGBA, then you would actually have an alpha value as well. So let's say it's half see-through, let's say 128. So that pixel will be half see-through. It'd be a white pixel, half see-through. Full red, full green, full blue, and then half see-through. And that would be a 4 bytes per pixel. So if you had a 4K image, let's look at a 4K image. A 4K image is 3840, and this is how you work out the file size, width and height. If it was a 32, so RGBA, which is 32-bit, right? To work it out, you multiply all those together. That's going to give you the number of bits, okay? And then you obviously divide it by 8 to get the bytes. So the number of bits is that times that times that. That's the number of bits, and obviously you do that divided by 8 to get the number of bytes. So a 4K single image is, hold on, would be, if it wasn't compressed, which it will be, but 33 meg for just one image. So you can see how much that is, quite a lot. So yeah, the rest of the, so your work is to complete this worksheet here. So you can find the information. I've got the formula here. So you just watch this video again, complete out this document, and that's what you've got to do. There you go.